All right, so this is the lesson on Le Chatelier's principle. Exactly what that is will be explained a little bit earlier. It has something to do with shifts in chemical equilibrium. All right, so let's do a little review of the last unit. Recall the 5 different factors that affect the rate of a reaction. Now, the nature of the reactants, that can't be changed, all right? Because you can't just switch up the compounds. That would be a different reaction. So let's not consider that one. The other 4, you would have the concentration, temperature, surface area, and catalyst. So we're going to look at 3 of these and see what we can do to affect the rate of reaction so that we will disturb the equilibrium. So recall, equilibrium is when the forward rate of reaction is equal to the reverse rate of reaction. But what if we manipulate something, we increase or decrease the rate of the forward or reverse reaction so that they're no longer equal, so they're not at equilibrium anymore? What would happen then? All right. How would that affect the equilibrium? What would the thing do to reach equilibrium again? So these are the questions that we're going to investigate. How? Well, using Le Chatelier's principle. Okay, so we can predict what happens to an equilibrium using this principle right here. So Le Chatelier's principle, in the long version, is when a chemical system at equilibrium is disturbed by a change in a property, then the system will adjust in a way to oppose the change. And when you change something, the system will change it right back. The short version of this is whatever you do, nature tries to undo. Okay, you want to increase something, well, the system will decrease it. You want to go to the left, well, you go to the right. You want to go up, well, you're going to go down. So Le Chatelier's principle will always seek to undo what you just did. Whatever stress you apply to change the system, it will be undone. When you disturb the initial equilibrium, so you reach equilibrium, you have it, then you do something to disturb it, temporarily there will be non-equilibrium, so you won't be at equilibrium anymore. Then something will happen, and then a new equilibrium will be established. And that something is what we're going to learn. So how do you disturb a chemical system? Well, 3 ways. One is you can change the concentration of something. It could be reactant or product. Then you will change the rate of reaction. Therefore, you will change the equilibrium. Or you can change the temperature of the reaction, and that will matter. And we'll talk about that a little bit later. Lastly, and this only applies to gases, change the pressure. Okay, if you don't have a gas, then changing the pressure does nothing. All right, so one at a time. Let's start with changing concentration. If you add or remove some products or reactants, you will change the concentration and you will result in an equilibrium shift. Okay, what is an equilibrium shift? Well, if you screw up the equilibrium, something must be done. In this case, you will change the concentration of reactant or product so that equilibrium will be restored. All right, you have to basically rearrange the concentrations of everything so that you will have a new equilibrium. How? Well, here's how. The addition of a reactant or product will cause the reaction to proceed in the direction that will consume this newly added substance. Does that make sense? If I add more reactant, then I'm adding like fuel to the fire of that reaction. If you add more reactant, you're increasing the concentration. You speed up that reaction to produce more products, thereby consuming that added reactant. Does that make sense? So overall is you will consume it right after, and the addition will just go right back down. So you add a reactant, the system will shift in a way so that you will consume that reactant. It will undo what you just did. but there will be other ramifications, like you will produce more product. You see what I mean? If I give you, I don't know, here's $100. I pick a student, I give you $100. You'd be like, oh yes, and then you will be more inclined to spend that $100. So I am encouraging action to consume that $100. So you got something, you consume it. Similarly, if you remove a reaction or product, then you discourage that reaction. That will become slower because you reduce the concentration. All right, so that means the equilibrium will shift in a way that will produce the missing substance again. Okay, so always what you do, the system will try to undo. So let's look at specific examples and see what I'm talking about. So consider this: carbon dioxide decomposes into carbon monoxide and oxygen. All right, so this is an equilibrium reaction. In the beginning, if you look at the graph, the yellow part, you have all carbon dioxide, no products. So the carbon dioxide will start to break down, and the rate will slow and slow until it reaches 0. And the products will increase and increase until the rate reaches 0. Well, the rate of change reaches 0, I should say. And then you reach equilibrium. Okay, you have 3 different concentrations at equilibrium. Cool. And then I disturb the system. How? I add more CO2. And if you look at the graph, that dashed vertical line is when I added the CO2. Notice that the red graph spiked a little bit. That spike is the result of the addition of more CO2. So now you're not at equilibrium anymore. You changed the system. How? Because now you have more CO2, the forward reaction will have more fuel than the reverse reaction, so it will win. So CO2 increases, this increases the rate of the forward reaction. So if you look at the equation, the forward arrow now is bigger because it's becoming faster. And if that becomes faster, you will be more efficient at making products than the products are making reactants. And so as a result, you will make more product and you will consume carbon dioxide to do so. Does that make sense? You will, more products will be produced than consumed. So this results in a net decrease of CO2 again, coupled with an increase of CO and oxygen, the product. And when you reestablish the new equilibrium, you now have more products. So we say that the equilibrium shifts to the right to favor the products because you're increasing the products. Is that clear? Notice the Le Chatelier's principle here. Whatever you do, nature tries to undo. What did you do? Well, you added CO2. What did nature do? Well, ultimately decrease CO2 by making more products. You see how this works? You good? Great. Here's another one. Same reaction. Same chemical equation. Same story. You start with all CO2, no products, and then you let it run, and then you reach equilibrium. Okay, cool. Now, remove some carbon monoxide from the product. All right, so look on the graph. The green curve has a huge drop. It fell off a cliff. And then you disturb the equilibrium because now you're missing some products. Because CO drastically dropped, the reverse reaction slows down because you now have a lower concentration. The forward reaction doesn't change. As a result, rate forward is now bigger than rate reverse. And this imbalance will result in the net gain of products because the forward will beat reverse. You see what I mean? And more products will be produced, meaning that more reactants will be consumed. You will decrease CO2 coupled with an increase of CO and an O2. So when you reach equilibrium again, the new equilibrium, we say that the equilibrium shifted to the right side to favor the product because now you're making more products. You see what I mean? Again, Le Chatelier's principle. Whatever you do, it seeks to undo. What did you do? You remove CO. What did nature do? Look, increase CO, the opposite of what you did. And also there's other effects, like you increase oxygen too, and you also decrease carbon dioxide. So does that make sense, guys? This is Le Chatelier's principle with concentration changes. Questions? All right, good. So this is a real experiment that I planned on doing with you guys. This is one of the coolest experiments because you can see drastic color changes and you wouldn't expect those color changes. But too bad, coronavirus, we can't do it. So here is a rundown of what you would have seen if we did it. So this is a very interesting reaction. You have iron 3+ ions, which is a colorless solution, I'm told. But when I actually did this, it kind of had a yellow tint to it. Thiocyanate ion, SCN, that is a colorless solution. When you mix a really pale yellow solution with a colorless solution, you would expect the solution to be a pale yellow, right? No. When you mix them, you will produce FeSCN2+ ions, the iron thiocyanate ions. Those are crimson dark red. So when you mix these two together, you're going to have this beautiful dark red color, like wine. That is an equilibrium reaction. All right, that color is in equilibrium with the other colors. Now let's disturb the equilibrium. So with part B, you take a dropper and you add some iron 3+ into your test tube. Iron 3+, I told you, has basically no color. It's like a pale yellow. If you add pale yellow to a dark red solution, what would you expect the solution to turn? Probably more pale, right? Because you're adding a more pale color to a dark color. Art will tell us that, well, the hue should become lighter. In fact, it does not. What's surprising is if you add more pale iron ions, you will make the crimson color even darker than before. You increase the shade of redness because of Le Chatelier's principle. Right? If you look at the graph in figure B, if you spike up the concentration of iron, then Le Chatelier's principle will seek to reduce the concentration of iron. How? By making more product. The equilibrium will shift to the right side to make more product so that you will lower the iron concentration again. And this increases the FeSCN2+ ion, which is dark red. If you increase that, you become darker. You see what I mean? So that's the weird part about this. You add a light color, it actually becomes darker. That's why it's so cool. Now, if you add the SCN ion, same story. SCN is a colorless solution. If you have a red solution and you add like colorless solution to that, wouldn't you think you would dilute it to become less red? No, the same thing as before happened. It becomes darker still for the same reason. In C, you spike up SCN concentrations. Le Chatelier's principle would then seek to reduce that by making more products. So you shift the reaction to the right side, you produce more of that crimson red ion to consume the additional SCN. So now you become even darker than before. Okay, and lastly, D, you now have a really dark solution. What happens if you add more of that dark solution? So iron thiocyanate is now being added. You might think, I have a dark red, I add more dark red, it's going to be darker or stays the same, right? No. If you add more dark red ions, in fact, it will become lighter due to Le Chatelier's principle again. Because now you're increasing the iron thiocyanate ions. Okay, so now you force the equilibrium to shift to the left because Le Chatelier will want to decrease that again. If you decrease the product, you favor the reactant, you produce more reactant, which has a lighter color. That will actually make it lighter. Now you see how Le Chatelier's principle plays a role in this? You basically get the opposite of results of what you add. If you want to make it darker, add the light color. If you want to make it lighter, add the dark color. All right, so here is a text version of what I just said. You can just read that again on your own time. I basically summarized this already. Let's look at some examples of this. So example 1, you need to know how to predict the effect on equilibrium on certain reactions. And here's one example. So carbon dioxide mixed with water, you have H3O plus and the bicarbonate ion. What happens to the equilibrium if you increase the acidity of the system? Okay, what does it mean by increasing the acidity? Do you see an acid in here? Can somebody tell me where's the acid? I'm guessing you guys didn't learn this. In grade 10, we learned that an acid is H plus, right? Hydrogen ions, that's the definition of an acid. Well, we didn't yet learn the grade 12 version of an acid. It is H3O. In fact, H plus does not exist. It will bond to a water to make H3O. That's acid. Okay, we will learn that in the next section. So, increasing acidity means you will increase H3O plus. Okay? What happens then if you increase H3O plus? Which direction will this shift, left or right?
Left.
Left, you sure?
No.
No. Oh. Be confident. I'm trying to mess you up here. It's to the left. All right. If you increase H3O, you basically promote the reverse reaction. And now the reverse reaction will be faster than the forward reaction because you increase the concentration of the product. So this results in the net loss of acid because, in Le Chatelier, you increase acid, well, I'm going to decrease acid. So CO concentrations will go up because you will make more reactants. As a result, the acid and the carbonate ion will decrease. Okay, again, Le Chatelier's principle at work here. The equilibrium, therefore, will shift to the left side to favor the reactants. Okay, notice I didn't put an arrow for the water. I never said that water increased in concentration because water is a pure liquid. We do not consider pure liquids in our equilibrium. That's why I just ignored that altogether. Okay, so do we have any questions? All right, cool. Example 2. Sulfur trioxide decomposes to sulfur dioxide and oxygen. All right, so what happens? Predict the effect on the equilibrium if you increase SO3. So you increase this. Equilibrium shifts left, right. Which one? It might take a while in the beginning. Again, Le Chatelier, always in the opposite direction. You increase SO3, I'm going to decrease SO3. So which direction is that?
Right.
The right side. The only way to decrease SO3 because of Le Chatelier is to use it up. By making more product, you will favor the production of the product because you increase the rate of the full reaction by increasing concentration. So you have a net gain of products and a loss of reactants. Because again, Le Chatelier, if you increase that, you will decrease it. All right, so this will favor the right side, which is the product side. Always favors the opposite sides of what you added. and always favors the same side as you subtract it. That's how I remember. I could do this in 1 second because I just followed that rule. You come up with your own special way of remembering this. But I do expect you to predict what happens to the equilibrium if I change the concentration of one of these things. All right, so any questions? All right, so let's move on to changes in energy. By energy, I mean temperature, kinetic energy. If you have, let's say, an endothermic or exothermic reaction, there will be an energy in the equation, right? It's either in the reactant or product. You can treat this as if it is a reactant or product. Well, it is a reactant product, it's just not a molecule. It's a number, it tells you the kilojoules. So endothermic, you would have the reactants plus energy to give you the products. Okay, you need to consume energy in the reactant to get to the product, hence endothermic. Exothermic, you have the reactant releasing energy as a product with the products. Okay, so please make sure you know that. Now, you can add or remove energy from a system simply by heating or cooling the system. If you heat the system, you input energy. If you cool the system, you remove energy. Okay, in either situation, though, equilibrium will shift to undo what you just did, to minimize the change. If I heat it up, Le Chatelier will seek to cool it down. If I cool it down, Le Chatelier will seek to make more energy. Example would be this. We talked about this in the last class. N2O4 and NO2. NO2 is a brown gas, and N2O4 is colorless. This is an endothermic reaction, the decomposition of N2O4 into NO2. So you have a colorless gas, you add some energy, it will break into this brown gas. It depends on where you put it. If you put it in the hot water bath, that means you increase the heat, the equilibrium shifts to the right, you have more brown produced, the product. If you put this in an ice water bath, you reduce the temperature, so you will shift equilibrium to the left, producing more of that colorless gas, and less brown, you will become less brown. So on the left in the picture is the cool water bath, on the right is the hot water bath. You can clearly see the differences in the colors. Right? This has to do with the equilibrium shifts. Okay, so temperature does affect the equilibrium. Looking at a specific example right here, SO2 gas plus oxygen gas, equilibrium, you get SO3 and energy. So this is exothermic. You start with all reactants, no products, and you eventually reach equilibrium. They all stay the same now. Okay, cool. Let's disturb the system. Let's decrease the temperature. If you decrease the temperature, you will decrease the rate of reaction, right? We've learned that before. However, the forward and the reverse will decrease at different rates. The reverse reaction will decrease more than the forward reaction. So as a result, the forward reaction after you slow them down will be faster than the reverse reaction now. Okay, and if you look at this graphically, how do you know that the temperature changed? Well, if you look at the graph, all three concentrations stayed the same, but they started changing together. That indicates a change in temperature, which applies to everybody. In the previous example, you see a spike or a drop in one of the concentrations. That means you change the concentration. But this one, there's no big spike. It's all gradual, so that means it's a change in temperature. And make sure you know how to recognize that. You might be asking, why? Why would these change at different rates? Right? If I decrease the temperature, it's easy to understand that the entire rate of the reaction will slow down. The forward and the reverse will slow down, but the reverse slows down more. To understand that, it's simply the reverse reaction is endothermic. It requires more energy than the exothermic forward reaction. Right? The forward reaction only needs a little bit of activation energy because it's exothermic. So if you decrease the temperature, a lot of them still have that activation energy, so you can still progress. It's slower, but still you substantially have enough products. But if you're endothermic, you got to get over a really big hump. That is a huge activation energy barrier. If you have good temperature, then sure, you can get over that barrier. But if you drop the temperature, you need a lot of energy. You need it more desperately than the full reaction, so you are affected more. You will slow down more. Does that make sense? If I become the dictator of the world, which I intend to try, then I will levy a tax on everyone on Earth. Everyone is going to pay me $1,000 per month. Okay? Obviously, this would affect some individuals more than others. If you're poor, if you live in poverty, me asking you for $1,000 a month or death, I don't think you can cough up that money. So you can scramble to get me $1,000, but that's going to be very difficult, and it's going to be a very tragic life for that individual. If you're Bill Gates, I don't think Bill Gates will even bat an eye. $1,000, he doesn't even care. Y'all gave me $1,000, but this affects different people differently because $1,000 means different things to different people. Okay, Bill Gates walks on the side of the road, sees like 10 grand, probably won't even bother, just keep walking because it's not worth my time. Okay, but the time and the effort he spends making that money, he probably could just make more money. But me seeing $1,000, ain't nobody stopping me. Okay, so very different. It depends on who you are. So here, endothermic, exothermic, very big difference. The reliance on temperature is different. Okay, so you decrease the temperature, you screw up the reverse reaction a lot more than you screw up the forward. So forward now wins. So lose energy. The reverse reaction is now a lot slower. The forward reaction was only a little bit slower. So you have more products produced because the forward reaction is now beating the reverse reaction. So you have a net increase in the products and a net decrease in the reactants. So you see the logic here? Hence reflected in the graph. So Le Chatelier's principle does the opposite of what we just did. What did we do? We decreased the energy. What did the system do? Increase the energy again by making more products. So equilibrium will shift to the right. Because you decrease energy, I'm now going to make more energy, so energy is on the right side, you shift to the right. Okay, does that make sense, everyone? I'm not hearing any questions. This is quite complicated, so I'm taking that as a good news. All right, so another example of changes in energy, you have CO2. The decomposition of that with energy to become carbon monoxide and oxygen. Okay. Initially, you just have CO2, no products. You let it sit, decomposition occurs, and then you reach equilibrium. Let's disturb it. So I'm going to decrease the temperature of this reaction just like I did for the last one. So temperature is now decreased. But this is an endothermic forward reaction. So as a result, the endothermic reaction is screwed over more than the exothermic. So the forward is screwed over more than the reverse. So now the forward rate is now less than the reverse. Okay, does that make sense? The reverse, since it's faster, it will produce more reactants than the reactants can be consumed. So reactant will go up, products will go down, and there you have it, Le Chatelier's principle. I decrease energy. Le Chatelier will shift the system so that it will produce that energy again. So equilibrium will therefore shift to the left side. Okay, did I make myself clear? How changes in energy affects equilibrium. All right, let's summarize this. You can have exothermic or endothermic reaction. So if you cool an exothermic reaction, forward and reverse both slow down. Okay, the rate of reaction slows down, no question about that. But the reverse rate, the endothermic one, will decrease even more because it needs more heat. So therefore, more products will be produced, equilibrium shifts to the right. If you cool an endothermic reaction, again, both forward and reverse will slow down, but the forward will slow down more because it requires more heat, being endothermic. Therefore, you will make more reactants because you suck at making products now because you're endothermic. So equilibrium shifts to the left. All right, so that's the effect on temperature. That's the effect on equilibrium with changing temperature. Now you can heat this up and the opposite would occur for both situations. So let's do this example then. So predict the effect on the equilibrium of both increasing and decreasing the temperature of this system. So look at the equation carefully. Energy is found in the reactant. So if you increase the energy, what happens? Can somebody tell me? Anyone? Increase the temperature. No? If you increase the temperature, I'll explain again, you can see that the heat is found in the reactant side. If you increase the temperature, that means you will favor the production of more product since you are providing the energy that the endothermic reaction needs. Another way of looking at this is you increase the temperature, Le Chatelier will therefore decrease the temperature. How would you decrease the temperature? Well, just use it up. Use up the energy to make the product, and you will decrease the temperature again. Okay, so that will shift to the right if you increase temperature. But what about when you decrease temperature? What will happen then, folks?
It'll shift to the left.
It'll shift to the left, just like we talked about before. If you decrease the temperature, because you're endothermic, the forward reaction will be greatly crippled. So the reverse reaction will become a lot faster. You produce more reactant, you shift to the left. All right, I guess the increasing temperature is a little bit hard because we never talked about that as an example, but it is the same idea, just applied in the opposite direction. And so you need to be able to just determine what happens to the equilibrium. If I change the temperature, well, I have to give you whether the reaction is endo or exothermic in order to do that. Okay, here in asterisks, it's something that people tend to forget. If you change the temperature, you're going to change the value of the KEQ. In fact, the temperature is the only factor that can change the KEQ. You can change the concentration all you want. The KEQ will always be the same. But if you change the temperature, you will get a new KEQ. Okay, so that's why in the future, a lot of example questions that I give you on the test, I will give you the temperature of the reaction. You will never need that number. You're never going to have to plug it into any equation. I will give you the temperature solely for the purpose of telling you that the temperature did not change. Okay, it's important that the temperature doesn't change, otherwise you change the equilibrium. So temperature is the only thing that changes KEQ. Let's move on to pressure. All right, so pressure, according to grade 11 chemistry, we learned pressure in grade 11. Boyle's law is one of the laws that we learned. Boyle's law says there is an inverse relationship between pressure and volume. Increasing the volume means decreasing the pressure. Okay, decreasing the volume means increasing the pressure. Just think of a balloon. Squeeze on a balloon, you decrease the volume, increase the pressure, you have the risk of popping it. Now, here's a really key statement. Changing the volume of any equilibrium system involving gases may cause a shift in the equilibrium. may cause. Okay, why would we use the word may? Is that on purpose? Drinking cyanide may cause death. Did I say that correctly? No, drinking cyanide will cause death. Okay, it's not a probabilistic event. You drink cyanide, tell me when the funeral is. There's no way you can survive that. Walking blindfolded into traffic may cause death. That's correct. Okay, if you're lucky, no cars hit you. Okay, right now, not a lot of cars on the road. Just walk blindly into traffic. You could survive, or you could die. Like somebody could hit you, and it wouldn't be their fault. So don't try this. May being probabilistic, it could happen, and maybe not. Okay, so if you change the volume of a system with gases, you may cause a shift. Not necessarily will, but may. Well, what does it depend on? It depends on how many moles of gas of the reactants you have and how many moles of gas in the products you have. You have to count the total moles of gas in the reactants and the products, and you must compare them. Okay, whether there is an effect depends on the numbers. Let's check out this example here. Consider here the Haber process. Again, nitrogen, hydrogen to make ammonia. Okay. If you count the moles in the reactants, you have 1 mole of nitrogen, 3 moles of hydrogen. Those are your reactants. They combine for a grand total of 4 moles of gas in the reactant. Cool. Let's compare that to the products. I have 2 moles of ammonia. That's it. Okay. 2 moles of gas in the product. So there is more gas in reactants than products. Okay. Let's imagine that I push the thing down so that the gas is occupying a smaller volume. I reduce the volume by 1/2. Well, this will result in a doubling of the pressure. So okay, I doubled the pressure. What happens? Which direction will this equilibrium shift, if at all? Anyone want to take a crack at this? No? Think about Le Chatelier's principle. What did I just do? I increased the pressure. Okay, so what would Le Chatelier want to do? Decrease the pressure. You see, always the opposite. So how would you decrease the pressure? The only thing you can do is forward or reverse reaction. To decrease the pressure, you need less gas. To get less gas, all you have to do is make more products because the products have less gas than the reactants. So the forward reaction will be heavily favored over the reverse reaction. So the equilibrium will shift to the right to produce less gas, lowering the pressure. Okay, so this will favor the products. Is that clear? When you have a bunch of gases and you change the pressure, Le Chatelier's principle will favor one side over the other to counteract that change in pressure. If you increase the pressure, Le Chatelier will decrease it. If you decrease the pressure, Le Chatelier will increase it by making more gas. Okay, which is why I said that this depends on how many moles of gas you have on each side. If you happen to have equal moles of gas on each side, then nothing happens. You can increase the pressure, but nothing's going to happen because they increase the pressure equally. All right, so that's why I said there may be a change. So there must be differences in the moles of gas in the product versus the reactant. So is this clear? Any questions? Y'all good? All right, so let's look at this graphically. You have SO2 and oxygen. You make SO3. So all of these are gases, okay? In the beginning, you have only reactant, no products. You let the thing run and it reaches equilibrium, good. They all have constant concentrations now. So let's shrink the container. You decrease the volume, that means you increase the pressure. When you increase the pressure, the concentration of everyone in the container will increase. All right? Because they're all in the container, and if you make the container smaller, you don't change the amount of gas, everyone's concentration will go up. That's why in the graph you see a spike in everyone. Everything spikes because there is a decrease in volume. So increase in concentration of all the gases, only the gases. If you're not a gas, you're not affected. Okay? All right, so if you increase the concentration of everyone, then you will increase the rate of reaction for everyone. This is the opposite of decreasing temperature. If you increase the concentration of everybody by decreasing the volume, then the reverse and the forward reaction will become faster. But again, life is not equal. The forward reaction will increase more than the reverse reaction because the forward reaction will experience a greater increase in pressure. You see what I mean? Therefore, you will favor the product side, the side with less gas. Products will increase. The equilibrium will favor the product side. It shifts to the right side. Right, if you look at the graph, SO3 will drastically increase because of the increase in pressure and then slowly increase because of the equilibrium shift. Whereas the other two, they both have a drastic increase, but then a slow drop as equilibrium is reached and they're consumed again. Okay, so that's the effect of pressure on the equilibrium only for gases and only if those gases are not equal in the products and the reactants. All right, so let's move on to the last one, the addition of a catalyst. We learned in the last unit, and here's a potential energy diagram. A catalyst will reduce the activation energy for the reaction. This reduces the activation energy for both forward and reverse reactions by an equal amount, meaning that both forward and reverse are sped up by the same rate. So the reaction is now faster, but nobody's winning. It's like Alice in Wonderland. You run faster and faster to stay in the same place. So you don't change the amount of concentrations of products and reactants, so there's no effect on the equilibrium. So the catalyst will have no effect on the equilibrium shift. You simply make the reaction go faster, but equilibrium doesn't go anywhere. Does that make sense? The last little bit is the addition of inert gas. If you add an inert gas, like a noble gas, like helium, for example, it's not going to react with the content of your container. All right. All it does is it gets in the way. Remember collision theory? Things have to collide in order for reactions to happen. Well, if your container is full of helium, you could collide with the helium and waste that collision. That does nothing. Helium will not react with you. So they just get in the way of the reaction. But helium will get in the way of everyone. It's not selective in who to block. So everyone is affected by the inert gas. So the reaction slows down, but the equilibrium doesn't shift because everyone's pissed off equally. Does that make sense? So addition of an inert gas does not shift the equilibrium. All right, that was a lot of information. So let's actually use what we've learned to see whether you can do example 4 and example 5. Example 4 is easy. Example 5, not so much. Let's do example 4 together. Consider this reaction here. Look carefully at the reaction. And then A, B, C, D, E. Tell me what happens to the equilibrium. A, if you increase the temperature, does the equilibrium shift to the left, to the right, or no change? Can somebody tell me the answer?
Equilibrium shift to the right.
Shifts to the right. To favor the production of methanol and the 35 kilojoules of energy. Temperature is increased. It means Le Chatelier will decrease the temperature. You see what I mean? If you increase the temperature, the 35 kilojoule is increased. So then you would have to shift to the left to get rid of it. So the answer is left. If you shift to the right, then you increase the temperature even more, which is the opposite of what Le Chatelier should be doing. Is that clear? So these can be tricky. The examples I showed you are decreases in temperature, so I guess you thought of it that way, I guess. But if you increase the temperature, Le Chatelier will decrease the temperature by favoring the reaction that consumes energy, which is the reverse. You make more reactants, reduce the temperature. B, increasing the pressure, what happens? Left, right, nothing. So think about what happens to gases with pressure.
Shifts left.
Shift left. How did you get that answer?
When the pressure is increased. Like I got an example from the last example because like the energy was in the products, and when there are more reactants, like there are more reactants, that's why I was thinking.
I think you're reading it wrong. Now pressure increase versus volume increase is the opposite. Because your increase in volume decreases the pressure.
Oh, okay.
So yeah, the pressure,
right. Okay.
I mean volume decrease. So it's not left.
Yeah, okay, that's right.
Right. Yeah, I guess you just read one word wrong. If you increase the pressure, Le Chatelier will decrease the pressure. Right? How would you do that? Well, move it to the right. The right side has just 1 mole of gas. If you just make more of that, you decrease the pressure by making less gas. All right. What about adding H2? Left, right, nothing.
To the left. I mean to the right.
To the right. Okay, thank you. That scared me there. If you increase the amount of hydrogen, you increase the concentration of the reactant, which results in an increase in the forward, but not the reverse. So you go to the right. You consume that hydrogen again. All right. These, just think of it as whatever I increase, I will consume. Whatever I decrease, I will make more of. Let's say, for example, I don't know, Ivy, you've been a great student, so I just want to give you some money, just to encourage you, right? So here's $1,000. Okay, that's too much. Here's 1,000 Vietnamese dong. All right. You take that large sum of money, you'd be like, oh, I can't take this for my own. I'm going to share it with the rest of the class. So you distribute that money to the rest of the class. Everybody else gets the money. You lose money. So that's Le Chatelier. I give you money, you lose money. Make sense? If, let's say, I don't know, Calvin walks on the street, makes a bad turn, goes into a bad neighborhood, gets robbed blind. He comes back and is like, oh, I just lost all my money. Now I have no money for lunch. And the classmates like, oh, well, I feel so bad for you, Calvin. Everybody chip in, give him $1, and then he gets the money back. So what happened? He got robbed, he lost money, and he got the money back.
Well, everyone else lost money because Calvin got robbed. Okay, that's Le Chatelier's principle. If you decrease something, that will increase again, and you will do that by consuming other things. D, neon. If you add neon, what happens?
Nothing change, like no shift.
Nothing, exactly. Neon is a noble gas. It's inert. Adding neon does nothing. Okay, catalyst. That's like the easiest one. We just did that one. Remember, catalyst increases the rate of reaction equally forward and reverse. You see what I mean? Anyone?
No change.
The answer is no change. That's correct. If you increase the forward rate and then you increase the reverse rate, all you do is you make the products and reactants faster. But nobody's winning. It's like an arms race. The antelope runs fast, but so does the cheetah. Okay? Evolution would have the antelope run a little bit faster to outrun the cheetah because of natural selection, but then evolution will also make the cheetah run faster to catch up to the antelope. So that's why they both run really fast. That's an arms race. Same thing here. Nothing really happens. All right, you make the forward faster. Reverse also is faster, so really, you didn't change anything. Now, this example is actually difficult. There's a lot of tricks in here. So consider this. Okay, sodium chloride solid with some energy, and that becomes sodium plus ions and chloride ions. What happens if you increase the temperature, guys? Left, right, nothing.
To the right.
To the right, yes. It shifts to the right because the forward reaction is endothermic. It requires a lot of energy. If you increase the temperature, you provide that energy. So perfect. You would really favor that reaction to produce products. Okay, you can think of it logically too. This is common sense. If you try to dissolve some salt, this is what this reaction essentially is. Sodium chloride solid dissolve in water to become the ions. If you want to dissolve salt, and if you heat up your solution, you can dissolve more salt. Right? Solubility increases with temperature increases for most salts. And this is the reason, Le Chatelier's principle, because it's endothermic. Okay, increasing the pressure, what happens?
Shift left.
Shift to the left to favor the production of less reactant, right? There's 1 mole on the left, 2 moles on the right, so increased pressure, you shift to the left. You sure? I'll tell, that's what the morning class said too. Go to the left.
I think no, because like there's no gas in it.
Yes, thank you. That's why I'm giving you the 1,000 dong. No change because there's no gas. Pressure always affects gas only. If you don't have a gas, well, a solid will not be affected by pressure. Does that make sense? So nobody's a gas here, no change. That's a trick question. Okay, C, adding more sodium chloride.
No change.
Damn, you're on fire. No change. That's the trick. A lot of people answer, well, it will shift to the right because you're increasing the reactant, right? No, why not?
Because it's a solid.
I'll give you 2,000 dong. It's a solid. A solid does not have a concentration. It is not subject to change. Adding more solid salt into water doesn't mean you'll dissolve more if it's already saturated. You just have more solid salt. So that actually has no change. So please be very careful of the state of matter.
Aqueous and gas, adding more, it does change something, but solid and liquid, adding more changes nothing. Okay, that's the trick here. Our D is very difficult. Sodium nitrate is added. What happens?
No change.
No change, right? Because I don't see a sodium nitrate in here. That's tricky. It's not no change. There is a change. Think of it this way. In grade 11, you learn solubility. Sodium nitrate. You put this in a solution, it will dissolve. Okay, the sodium and the nitrate will break apart to make sodium plus and nitrate minus. Does that help? Sodium is always soluble, nitrate is always soluble, so this will dissolve. What happens?
To the right.
To the right. Why do you say that?
Because like if you dissolve it, then it creates like more ions, like sodium ions, and then it's also nitrate.
Yeah.
So I think that is gonna shift, like preferred more to the production, like the products, I mean.
You think about what you're saying. You're saying that you dissolve this, you will make more sodium ions, so you increase the amount of sodium ions, and this favors more production of sodium ions.
Yeah.
You see the conflict here? Le Chatelier's principle. What you add, you will subtract. So you have the right logic, just it shifts to the left.
Okay.
You increase the amount of sodium ions by dissolving that thing. Right? Sodium plus goes all the way up. So therefore, you have a higher concentration of sodium. You will favor the recrystallization of sodium back into solid form. Shifts to the left. Okay, increased concentration, Le Chatelier will decrease that concentration by using it up. Okay, that's the tricky part. You have to A, recognize that I will increase sodium ions because sodium nitrate will dissolve to make more of that, and then Le Chatelier will shift it to the left. E is the hardest. What happens? Lead 2 nitrate is added.
Is there no change because like the lead nitrate is insoluble?
Actually, lead nitrate is soluble. Any nitrate compound is soluble.
Does it shift left because there's more nitrate?
Why would having more nitrate shift it to the left?
Because I thought like when the lead nitrate dissolves in water, like more moles of nitrate is going to be produced. So
Yeah, for sure, yes. It's just that there is no nitrate in the chemical equation, right? How would that affect the equilibrium?
Would it shift right?
Shift right? Why would you say that?
Because if it dissolves, doesn't it increase the temperature? Because there's like...
No, okay, you're really doing this in a sneaky way. If it dissolves, I don't think it increases the temperature. I think it decreases the temperature. Actually, I don't know whether that's endo or exothermic. But let's not consider that. Now, I haven't even thought of that. Okay, that's a good one. But yeah, let's not think about the temperature here. Just purely look at the ions produced. You have lead 2 plus ions produced, NO3 1 minus produced, right? You compare it to the equation. I have none of those. So why would that matter? So far, nobody said the right answer. Well, Calvin did say the right answer, but for the wrong reason. It shifts to the right. Okay, why does it shift to the right? That's where the tricks come in. Nitrate doesn't do anything. Nitrate does not react in solution, it stays there. Lead, however, lead 2 plus will be made, and lead is highly insoluble. Okay, lead 2 chloride, if it sees a chloride, it will bond with it and precipitate as a solid. You will drastically reduce the amount of chloride in the solution with lead. So you decrease chloride, Le Chatelier will increase chloride by dissolving more sodium chloride. So it shifts to the right. Okay, you see how this works? This is quite tricky because you have to know the solubilities of these substances, and you do have the solubility table. In the booklet I gave you earlier in the course, one of the pages is a solubility table that tells you which compounds are soluble in solution. All right, I just want to touch on this today while we learn Le Chatelier's principle. There will be a lesson on solubility equilibrium, which will explain a little bit more on this. Okay, so far, is that good? So these can get confusing, left, right, or nothing. So please make sure you guys really get this down. Learn how to predict using Le Chatelier's principle. This is extremely important. I can't stress this enough. We will be doing a lot of Le Chatelier's questions throughout the rest of the course as part of a bigger question. So we will just brush right through, like 2 seconds. You can tell me left, right, okay, let's move on. So you need to really hammer this home. So we just learned the Le Chatelier's principle today. That's it, equilibrium shift, and how the different stress factors can affect equilibrium. This table summarizes everything. Concentration, temperature, volume, how that can change the equilibrium and how the equilibrium will shift to get it back. And then no effect is catalysts and inert gases. All right, questions? No? Alrighty, I'm going to stop.